It's time to shift gears and start focusing on the objects in space again. For the next several chapters, we're going to be looking at stars. We'll start by looking at the properties of our own sun. Then we'll look at other stars and see the range of different properties they can have. Finally, we'll look at how stars evolve, how they form, live their lives, and die, as well as the bizarre corpses they leave behind. But to start off, let's focus on our own sun. This is a good place to start for two reasons. First, it's close enough to us that we can study it in detail. There's a tremendous amount we can observe directly in the sun that we can only infer about other stars. The other reason is that it's a very ordinary star. As such, by studying the sun, we're really getting a picture of the most common type of star in the galaxy, a main sequence star. We're going to start out by looking at how we study the sun's interior, since we can't see it. We'll also see what we can deduce about the structure of the sun. Next, we'll see how heat flows inside the sun. After that, we'll talk a little bit about the sun's surface, especially the clues that it gives us about the interior. Then we'll make a slight detour to look briefly at Einstein's special theory of relativity. That will give us a better understanding of our final topic, how the sun generates energy through nuclear reactions in its core. We can't see directly into the sun's interior, but that doesn't stop us from figuring out what it's like inside. We can combine the things we can directly observe along with our understanding of the physics of matter and energy to get a clear picture of what the sun's interior is like. There are several types of observations we can make about the sun's interior. These include its mass and density, which sets basic limits on what it's made of. We also know its surface temperature and the amount of energy flowing from its interior. This comes from a study of the sun's overall spectrum, like we saw in Chapter 5. We can tell the surface composition of the sun from more detailed spectra. This can act as a starting point for working out the composition of the sun as a whole. We can study the sound waves that move through the sun's interior and cause its surface to vibrate. This process, called helioseismology, lets us understand the interior density structure of the sun in much the same way that studying earthquakes lets us understand the Earth's interior structure. Finally, we can observe the neutrinos generated in the sun's nuclear reactions. As we saw in the last chapter, these can travel all the way through the sun and be detected here on Earth. They give us direct evidence of the nuclear processes going on in the sun's core. The sun is governed by all of the rules of force, energy, light, and matter that we discussed in earlier chapters. We can use this to constrain what the sun's interior must be like. For example, we know the sun's size and the fact that it's neither expanding nor contracting. This means that there has to be a balance of forces. Any forces pushing inward have to balance out any forces pushing outward. The main inward force is gravity. This is balanced against the internal gas pressure pushing outward. However, the only way pressure can push outward is if the pressure inside is higher than the pressure at the surface. So we know that the sun's interior pressure has to keep going up as you get deeper inside it. That means that both the temperature and density have to get higher as you get deeper into the sun. We can use these ideas to build up a model of the sun's interior. We can simply divide up the interior into lots of layers. In each layer, we make sure the inward force of gravity is balanced against the outward pressure. This determines what the conditions we like in the next layer down. And then we can apply the same approach to this next layer. We can check this against the densities we find from helioseismology. We can also use the amount of energy flowing through the sun's interior to determine how hot it is. We can get this heat flow from the energy the sun radiates into space. We can also use our observations of neutrinos to put limits on the amount of energy generated in the sun's core. Finally, when we finish putting together our model of the sun, we have to make sure that it still matches the overall density and mass that we observe.
You can get the main idea about pressure changes in either the atmosphere or the ocean from this your turn. If the weight of the Earth's whole atmosphere pushing down on sea level gives a pressure that we call 1 atmosphere, then what is the pressure at depth A? At depth B? Notice that we chose A to be 10.3 meters down, under a depth of water weighing just as much as the atmosphere weighs, and B is another 10.3 meters down. For you panicky folks, this is as easy as it looks. No trick question here, but do explain your answers. Now describe how pressure changes as you go up in an airplane. Modeling the pressure in the interior of the sun would be more complicated than modeling the pressure deep in the ocean, because the gas in the sun is much more compressible than the water in the ocean. Near the surface, where there isn't much pressure, a little gas takes up a lot of space, but deep inside, high pressure squashes the same mass of gas into a tiny volume, rather like the bottom pillow is the most squashed in the picture of the pile of pillows. In other words, the bottom pillow has the highest density, and with all that mass packed close together in the center of the sun, the gravitational force is large. To take account of all of this in our model, we'd end up with a challenging calculation. But for our purposes, it's enough to realize that the pressure and density in the solar interior are far greater than at the surface. Our model tells us that they have to be, or the interior would not support the outer layers. In the next slide, we'll look at the numbers.
When we put all these constraints together, it gives us a very clear picture of the conditions in the sun's interior. The temperature keeps going up the deeper you get into the sun. By the time you reach the core, the temperature is around 1.5 million Kelvin, a temperature close to that of the blast of a hydrogen bomb. In fact, this isn't a coincidence. The nuclear reactions occurring in the center of the sun are closely related to the ones used in hydrogen bombs. In most of the interior, the composition must be about the same as the surface, around 3/4 hydrogen and 1/4 helium, with a couple of % heavier stuff. The exception is the core, where there's excess helium. The weight of all the overlying gas squeezes hydrogen and helium at the core up to a density of 150 grams per cubic centimeter, or 150 times the density of water. There are a few materials on the Earth's surface that are even a tenth of this density. For example, solid gold is 19 grams per cubic centimeter, while lead is only 11 grams per cubic centimeter. Because the core is so dense, this is where the sun's mass is concentrated. The outer layers of the sun are very fluffy in comparison. One of the keys to understanding the sun's interior comes from looking at the way heat flows through it. All of the heat is generated at the core, and it all has to travel out to the surface, but the way that energy makes that trip depends on the conditions inside the sun. In general, there are 3 ways heat can flow through the interior of any object. The first and slowest of these is conduction. This is heat traveling through direct physical contact. Simply put, the fast-moving atoms in the hotter material bump up against the slower atoms in the cooler material, and the result is that the cooler material heats up. This is the sort of heat flow we experience when we touch a hot object, like a hot cup of tea. The sensation of heat we feel represents the effects of the fast-moving atoms in the cup. The next way heat flows is through convection. Convection involves heat moving because it's carried along by moving fluids. When you heat up a liquid or gas, it expands and gets less dense. If you heat it from below, then that less dense fluid will start to float upward to get above the cooler, denser fluid. So this will carry heat upward with it. If you heat up a pot of soup on a stove, you can watch this happening, with the hotter soup rising to the surface and the cooler soup sinking down to replace it. The last way to transfer heat is called radiative diffusion. In radiative diffusion, light carries the energy through the material. Remember that photons carry energy. Atoms emit light because of their temperature, and this light then travels until it's absorbed by some other atom. Then that atom emits the energy as another photon. This repeated emission and absorption causes the energy to travel in a random walk pattern through the interior. Radiative diffusion can be the fastest way to transport heat, but only if the material is hot enough. Remember that hotter objects emit a lot more light energy than cooler objects. In the Sun, radiative diffusion dominates the flow of heat through most of the interior. From the core to over 70% of the way to the surface, radiative diffusion is the main way heat travels. You might expect this to be fast, since it depends on light. But remember that the core of the Sun is very dense, and that radiative diffusion relies on random motions of photons. So in fact, it takes around 1 million years for energy to travel out of the core. In the outer layers of the Sun, the temperatures are low enough that radiative diffusion is no longer important. Instead, convection takes over as the dominant way heat flows. We can see the effects of this right on the Sun's surface. When you look at the Sun up close, you see a series of bright spots with darker rims around them. These are called granules, and they're the top layer of individual convection cells. You can see a map of North America superimposed on these granules here. If we watch over time, we can see hot, bright gas rising to the Sun's surface, cooling off and getting darker, and then sinking back into the interior. Click on the link to see an example of this. Finally, conduction is not an important process anywhere in the Sun. It's always slower than either convection or radiative diffusion.
Now you should fill in this table describing the 3 major ways heat can flow and where they are important in the Sun.